Okay, question 6 about logs. We can use our calculator. We need to find the value of log 1,000. Whenever there isn't a base number given there, we always assume it's 10. So I'm going to switch to my old calculator here because I suspect more of you have this type. So we have a button called log. This calculator doesn't show up so well. Okay, so I've just got log and I put in 1,000. And I press equals and I'm told it is 3. So that's quite straightforward. And now I've got log 1. I go back and log base 1, log base 10, just 1. So all I'm doing is putting a number in and, oh, and that's 0. And log base 3, 81. This time I have to find this other button here where I can put the base in. So here I am. Someone's about to come through the door. Okay, got rid of my visitor there. Okay, so now because we haven't got a base 10, which is the default, we have to actually pick the button. There we are, this button, where I can go in and I can say this time I want base 3. Use my cursor to come along. Is that showing? And I'm going to put 81 in the brackets. And it tells me the result is 4. So if you can use your calculator, then it's quite straightforward. But next bit, B, is asking you not to use your calculator, which means I expect to see some working. So now we need to know the value of log 100. Now this takes us back to what we did in class, where one of the definitions of logarithms is if we've got something called log A, log to the base A of B is x. So if that is true, then it follows that B is equal to A to the x. Okay, this A has come along and bumped x up into the air. So we can use this definition to solve that. So remember, if there's no base given, it's assumed to be 100. So let's say that's x, because we don't know what the value is, but that's what we want to know. So we bring the 10 out and bump the x up into the air. Now, it is very difficult to get an intuition around logs. They are a sort of artificial construct, so we just have to learn the definitions of it. I can give you the definition of logs in words, but it really doesn't help most students. So just learn this and then you can rearrange it yourself. So now we should be able to solve this sort of visually, because we think, what's the power of 10 that will equal 100? Well, it is 2. Can't put that in your calculator, but these kind of questions where you're having to calculate without a calculator will be quite straightforward. There'll be powers that you recognize. So x must have been 2. Let's say log base 2 of 16. Let's say it's equal to x, name our own variable. That means then that 16 is equal to the x. And if you don't recognize which power that is, you can do with a little bit of your calculator, you can say, right, I can say 2 times 2 is 4. That's not getting me there. Times 2 is 8, times 2 is 16. So I had to multiply by 2 4 times, which means x is 4. So 16 is 2 to the power of 4. And finally, we've got log 3 to the 27. That says equal to x. That means that 27 is 3 to the x, and that implies that x is 3, because 3 times 3 times 3 is 27. It's always going to be one of these low numbers. Using an approximation method, the famous approximation method, which I know you've done in Introduction to Economics, show that if income doubles in 17.5 years, then the average growth rate must have been 4%. So this is the famous 70 rule. So if we divide 70, a long story as to why it's 70, by 17.5, it will give us the approximate interest rate. So I'm just dividing 70 by 17.5, and it equals 4%. So 70 divided by the number of years gives you the rate. Also, if we say at 4%, how long would it take to double? We can divide 70 by 4, and we get 17.5. So we can use it both ways. So very useful approximation of the time it takes to double at a given interest rate. D. Now D, we're asking, or I'm asking you to use the rules of logs. If interest rates are 3.7%, find the exact number of years for an investment of 1 million to double. So that's like saying we've got 1 million. We are subjecting it to compound interest, 3037, and the R is equal to 3.7. So the compounding is 037. The first two digits after the decimal point are how many whole percent? So that's 0.7. Right, so we want to know how many years it will take for that to double. So here's me doubling the 1, whatever number that is, I would double that. But the unknown here is the number of years. At GCSE, you would always know how many years to put there, but we don't know. So we're going to have to put a variable. So we could say T, if we wanted, or N for number of years. So we're now going to use logs to solve this. We know we need to use logs to solve this. Actually, I'm just going to divide both sides by 1. Make this a little simpler. We know we have to use logs because, look, the unknown is up in the power. This is an exponential equation with an unknown in the power. Any other kind of algebra is not going to solve this. If the unknown's in the power, we know we need logs. So what do? We take logs of both sides. So here's me logging this side. Oops. 37t, and logging that side, because if that's equal to that, then the log of that must equal to the log of that. And then I'm going to use okay, and you will remember there is a rule of log which says that log a to the power of b is equal to b log a very important rule of logs. That's how we get to solve these exponential equations. So I know I can bring this b equivalent, which in this case is t, out of the log. That's the whole reason we use logs for this. Okay, and then now it's just t times a number equals another number. So as always, we can divide both sides by this number and get a value for t. If we divide both sides by log 1.037, that's just something we can put in our calculator. So let's do that. There we are. I'm going to do let's keep this shows up better. So using the fraction key, not showing up so well now. Fraction key, I'm going to say log 2 over log 1.037. So that's going to tell me how many years, and that's 19.08. So it's going to take, I've been asked to round my answers to 2 decimal places. Yeah, already have. So that's the number of years. Okay, so at that rate, it will take 19 years for any amount to double at that interest rate. So now I'm being able to do a little I'm being asked to do a little manipulation of logs. So I'm given that a equals b to the t. And I've got to show that log y is equal to log a plus t log b. So you'll notice we haven't bothered with any bases, so we're going to assume it's all log 10. So I look at this and my thought process is this is an exponential equation because the variable, the unknown, is up in the power. These lowercase letters are constants. I know it's not always obvious, but just imagine most things are a function of time. It's time that changes. These are just parameters that stand for constants. So I see t is up in the power, so I know I've got to take logs. I have no way of solving this otherwise. A, B, T. All right, that's well and good, but I would awfully like to get this T out of there, but I can't use this log A to the B equals B log A. I can't use that at the moment because there's this A in the way. So I need to use a different rule of log. Remember this one? So the log of A plus the log of B is equal to the log of A times B, which means I can break these two apart. So I can now say it's log A plus log B to the power of T. So I've used that rule. Now I can use this rule on this. I can bring that T out, which is what I want to do. Log A plus, here it is, log T log B, which is what I was supposed to show. So that's a very typical maneuver. That's how we take an exponential curve, which looks like that, and we turn it into a straight line equivalent. So the last bit of this is to do just that, is to think of that as a straight line. Oh, except we're calling it a wealth function. So this is yt, let's write it out, y0, y plus g to the t. So we're doing the same log maths as before, but we're calling it something else. So this is income at time t. This is income at time 0, or wealth at time 0, and g is the interest rate. Show by taking logs that yt can be plotted as a straight line. So you'll recognize this really. This is just the regular compound interest equation or formula. Time in the future, time at the beginning times the interest rate raised to the power of t. Yeah, it's just compound interest. So let's take logs of both sides because we've been asked to take something that's curved and turn it into a straight line. And we know we have to use logs for that. So I'm taking logs of both sides. But just like that previous one in part E, I need to separate these out. So I'm going to use this rules of log again. So log yt equals log of y0 plus log of 1 plus g for t. You see, it's exactly the same maneuver I've done. And the reason I split these apart is so that I can now use this power, this rule, and bring the t out. So here we go. Log yt equals log y0 equals t, oh no, not equals, plus t log 1 plus g. Now, you may not recognize it straight away, but this is a straight line graph. It is a linear function. So we can now recognize this. So this is f. We have done what we've been asked for. We've put it in the form of a plus b t. So this is just given as a general form. And we can see it fits the pattern. Log yt. We can see that log y0 is the a equivalent here, and we can see that b is really log 1 plus g. So we're just sort of seeing that it fits the general layout form of a straight line. And so finally, we've been asked to find what are the values of a. So a equals log. I've just noticed I've been misspelling log, I'm calling it yog. Oh dear. There's no such thing as yog. So a is log 0 because it's that constant thing. There's no t, there's no variable there. So it doesn't matter if it's there or there, it's the constant. And we know b is this thing that's multiplied by the t, the thing multiplied by the variable. So now we've been asked the last bit. So this is y, and now we ask, part 1, and then we want part 2. What is the gradient of the straight line? If this is indeed a straight line, then hopefully we can see that this is the gradient. Oops. Because it's the thing multiplied by the variable. And this is the vertical intercept. Because it's just a constant, there's no t there. So we could, if we got fancy, we could even just sketch this. So t is along the bottom, that's our x equivalent. Our y equivalent is log yt, i.e. the value of y at time t. And then what does this look like? Well, it's a positive gradient and it cuts the vertical axes at log y0. That's what our graph looks like. We have taken a curved, an exponential function and changed it into a straight line.